Modern global enterprise networks operate at an intimidating scale. Millions of connections fire across endless aisles of blinking hardware, moving massive data globally. To understand how a system like that actually works, we have to strip away the physical complexity and look at the strict academic definition of a network: a digital telecommunication system which allows nodes to share resources. A node is simply any individual device capable of participating in that shared digital space. The physical form factor of the device is irrelevant. Whether using a smartphone, a desktop PC, or a massive mainframe, architecturally speaking, they are all just considered network nodes. But an isolated node is functionally useless. A processor sitting alone cannot share resources with anything until a physical connection is established to at least one other machine. Understanding how a massive enterprise functions requires mapping exactly how we scale that basic connection across a sprawling corporate environment. We have to look at the specific hardware devices that govern data flow as a network grows from two localized machines to a globally distributed infrastructure. Connecting these machines is only the first step. Network engineering involves managing how these connections operate to ensure that every node can share its resources reliably. We build our models starting with the absolute smallest possible system, two isolated machines. By running a direct physical cable between them, we instantly cross the threshold from isolated hardware to a functional network. With the link established, one machine can ask the other for specific data. The node actively requesting that service assumes a specific role, the client. The node providing the requested file takes on the opposing role, the server. Because both of these devices sit at the ultimate edges of this data exchange, network engineers refer to them as end hosts. It is a common misconception that client and server are permanent hardware classifications, or that a server must be a massive rack-mounted appliance. In reality, an end host can operate as a client when it requests a file, and then immediately act as a server a microsecond later if another machine requests a file from it. Defining devices by fluid transactional roles, rather than plastic casing, is the prerequisite for tracking data flow through a complex system. That simple point-to-point connection works for two machines, but an enterprise department needs to connect dozens or even hundreds of end hosts simultaneously. Running a direct physical cable from every machine to every other machine in a 30-node department collapses the architecture into an unmanageable web. To solve this, we introduce dedicated aggregation hardware, the network switch. Every end host plugs directly into it. Looking at the front panel of a Cisco Catalyst 9200 enterprise-grade switch, its physical design maps exactly to its function. It features a high-density array of network interfaces specifically engineered to accommodate numerous local end hosts. By connecting these devices to a single switch, we establish a defined perimeter, a local area network, or LAN. The switch acts as the central nervous system, forwarding traffic exclusively between internal nodes plugged into its ports. While solving local aggregation, the switch creates a hard operational boundary. It has no inherent capability to route data to the outside world. A global enterprise requires entirely separate local area networks to communicate. We have a cluster of end hosts in New York and an entirely separate cluster in Tokyo. Since switches are isolated, a New York node cannot pull a file from Tokyo. We need a gateway to bridge these disconnected environments, a router. Sitting at the network edge, it faces the unstructured internet, bridging these isolated LANs. Contrast this with earlier hardware. Looking at the back panel of a Cisco ISR 900 series router, you see very few network interfaces. This low port density is intentional. A router isn't designed to connect 30 local desktops. It serves as a singular gateway to the internet. Data leaves the end host, hits the local switch, and is handed off to the router boundary, which then propels it out toward its destination. If switches are the hardware that build local neighborhoods, routers are the hardware that build the international highways connecting them. Building a highway directly into your local network introduces massive operational risk. The connection works in both directions. An attacker on the public internet can attempt to inject malicious data straight through that router bridge into the enterprise. We close that vulnerability by installing the final core piece of hardware, the physical firewall. Positioned at the perimeter, the firewall interrogates every piece of data crossing the boundary, comparing it against explicitly configured permit and deny rules. Modern perimeters rely on next-generation physical firewalls, equipped with advanced intrusion prevention systems designed to recognize and block complex attack patterns. This hardware appliance acts as the main gate. Backing it up, every individual PC runs its own software firewall as a secondary line of defense. Enterprise security is a nested architecture. We layer localized software defense firmly behind the hardened, rule-based physical gateway that protects the entire network. With our local aggregators, secure gateways, and international routing mapped out, we can trace exactly how an enterprise request functions in reality. A client in New York initiates a request to pull a file from a server in Tokyo. The request hits the local switch, which recognizes the initial local traffic and aggregates it for the next hop. The firewall inspects the outbound request, authorizing it against enterprise security policies before it can leave the network. The router then takes the authorized packet and catapults it across the wide area network boundary toward Japan. Upon receiving the request, the Tokyo server packages the required file and sends it sprinting back through the same hardware gauntlet in reverse to complete the transaction. Every global data exchange depends on this specific sequence of hardware. By orchestrating these discrete physical boundaries, we turn a collection of isolated devices into a cohesive system for sharing resources at a global scale.